Welcome, young students of chemistry. This is a quick recorded lecture on the condensed states of matter, condensed being, particles pushed together. So it's mostly about solids and liquids. We have spent this unit talking heavily about gases because they are very dynamic. Solids and liquids are not so much. So this corresponds with your note sheet on condensed states of matter. Please make sure that you have that out and ready and that you add the appropriate items. And then please make sure that you print the practice for the phase diagram worksheet that is on the website and do that in preparation for class. So you might want to take a minute to pause the recording and write this stuff down in your chart, and then we'll discuss it. So this is looking at solids, liquids, and gases at a particle level. It's important to remember that particle motion is what determines the state of the matter. And solid particles, tightly packed, they have a definite shape and a definite volume. Liquids also have a definite volume, and sometimes this confuses students. But I want you to think about this. If you have 2 liters of soda pop in a container and you spill it, it's no longer in the container, but it still is 2 liters of soda pop. So liquids also have a definite volume, but no definite shape. They take the shape of their container. And then gases, we know, have no definite volume or shape. The only thing that holds them together is the boundaries of their container. They will expand infinitely until something stops them. So with solids, there is slight motion, and any motion that's present in a solid is caused by vibrations of electrons. And we know that liquids and gases can flow, and that gases in particular are in constant motion. The effects of temperature and pressure with gases we have studied at length. And, we can pressurize solids and liquids. It's not a terrible, it's not a terribly effective thing to do in terms of making the particles closer to each other. We can pressurize a liquid to the point where it will exhibit solid properties. And we can demonstrate that in class with a little bit of cornstarch and water. But temperature with solids and liquids will cause thermal expansion if you're heating it. I don't know, when I was a child, jars had metal lids instead of plastic lids, and whenever something was too difficult to get open, my mom would tell me to run it under hot water, and what that did was expand the metal but not the glass, and therefore I was able to then open the lid. I know that lots of people say, oh, we should tap that lid with the edge of a knife or something. Ladies and gentlemen, that is not safe. Especially if you're dealing with a glass container. There might be teeny tiny particles of glass that get into that container. So if you've got a metal lid on a glass container, and this even works for plastic containers, you can run that under some hot water to expand that and then make that jar easier to open. Now, changes in state will occur if we change the amount of thermal energy that substance has. So any substance can exist at any physical state, solids, liquids, or gases. Things that are solid at room temperature can certainly be vaporized. Things that are liquid at room temperature or gaseous at room temperature certainly can be liquefied and then solidified. One thing I want you to remember about changes in state are the names. So fusion is an unusual name, but that refers to the state where we are either melting something or freezing something. And you can see here that something going from a solid state to a liquid state is clearly melting. What I want you to do is think about the movement of the particles and where we would put energy in that equation. So solid particles are moving slowly, or we should say have less motion. Than liquid particles do. So in order to make something that has less motion turn into something that has more motion, You need to think about whether we need to add energy to that something, or do we need to take energy away from that something. And in this case, we have to add energy. So energy here, I'm just going to, oops, is a reactant. So this is an endothermic process. Energy is required to be absorbed by the solid so that the particles are moving more and therefore become the liquid state. So then the opposite is true. If we are freezing something, going from liquid to solid, we're going from more motion to less. Which means that energy has to be removed from that substance. And where does it go? It goes to the surroundings. And that's what we call an exothermic process. Exo meaning out. So an exoskeleton, like maybe the Iron Man, has a skeleton on the outside. Many bugs have exoskeletons. You, ladies and gentlemen, have an endoskeleton. Okay, so the amount of heat that's required to make this happen is what we call the enthalpy of fusion. And I just want you to get used to this word, enthalpy of fusion, as being the amount of heat needed to melt or freeze something. We will look at enthalpy in more detail later. So looking at other phase changes, when something is vaporizing, it's going from the liquid state to the gaseous state. That's vaporization. And I want you to think about the particles of liquid and how they compare to the particle motion of the gas, and think in your head whether this reaction would, or I shouldn't say reaction, whether this process would require energy or if energy would be given off. So if you think about that for 1 minute, and the answer is energy is required. I hope you got that right. So this is an endothermic process. Whereas condensation or condensing is going from the gaseous state to the liquid state. And of course that is an exothermic process. We know that if we have a glass in the summertime, and maybe we have a cold liquid in there because that feels good to drink in the summertime with ice cubes in it, right? We know that sometimes we'll get little droplets of water on the outside of the glass. Right? Where do those droplets come from? Those droplets come from water vapor that is in the atmosphere. It hits the cold glass, and when it does that, it transfers its heat to the water and turns it into a liquid. So this gas, water gas, will transfer its heat to the glass, and the water vapor that's in the atmosphere turns into a liquid and sticks to the side of the glass, and that is called condensation. I think it's important for you to understand the difference between evaporation versus boiling. So vaporization would cover both of them. Evaporation occurs at the surface of a liquid. It's a natural process because you have these particles that are all moving around in there. Every once in a while, one of them gains enough energy to escape the liquid state and become a gas and then float away. And things that are volatile are things that evaporate really, really easily. It doesn't require much energy for that liquid to evaporate. Boiling, on the other hand, is something that occurs throughout the liquid. So when you're boiling, you have particles not at the surface, but somewhere else in the liquid that are going to get enough energy to become a gas, and therefore you'll see a bubble. And that bubble of gas escapes the surface of the liquid, becomes a gas, and floats away. Sublimation and deposition, these are a little bit strange. Most students are very familiar with vaporization and condensation, with melting and freezing, but sublimation and deposition are sometimes a little strange because you don't see it much. But sublimation is when something goes directly from a solid state to a gaseous state without ever crossing through the liquid state. So sublimation is a process that is energy absorbing, so this is endothermic. Deposition, going directly from a gaseous state to a solid state, is exothermic. That's giving off heat to its surroundings. Things that sublime, dry ice. If you get a piece of dry ice, it will automatically sublime. We will never see liquid carbon dioxide at room temperature and pressure. That does not mean it cannot exist, but under room temperature and pressure conditions, we won't see any liquid carbon dioxide. And then sublimation, or deposition, is something that you're probably a little more familiar with than you know. You just don't know the words. So when we have winter weather and we have snow or frost forming on windows, that is sublimation, and that's what gives us the beautiful crystalline snowflake structures. Everyone's their special snowflake. But, so we have water vapor high in the atmosphere. It deposits into a solid without ever entering the liquid state and becomes a beautiful snowflake or a beautiful frost crystal when that gas hits the cold window of your car and it transfers its energy to the window and it turns into that solid crystalline structure. Now we know that freezing rain is much different than snow or even, a frost. So freezing rain, the water comes down as a liquid and then it hits a surface and then it freezes. So we don't get those beautiful little crystals. What we get is just a sheet of clear ice, and that is a pain in the behind to deal with. So sublimation, solid to gas. Deposition, gas directly to solid. Okay, a couple of graphs that you need to be familiar with, and we're going to look more at this graph later on when we start talking about heat. But when a substance is in its solid state and we're adding heat to it, the temperature will steadily increase until that substance starts to melt right here. And then when it starts to melt, look at what happens to the temperature. The temperature remains constant. So the heat that's being added while that substance is melting, because we're still adding heat as we're going horizontally through the graph, we're still adding heat, but that heat is not being used to make the particles go faster, which is what temperature is. It's being used to break the particle attractions. Remember those intermolecular forces, London dispersion attractions, dipole attractions, and hydrogen bond attractions. So all of those are being broken until the very last particle is separated from its partner. Now we're not breaking the compound apart. H2O is still staying H bonded to O. We're breaking the attractions of one water molecule to another. But when those last two water molecules are separated from each other, then we'll see an increase in temperature again, as the liquid particles speed up and speed up and speed up and speed up until they become a gas. The first particle becomes a gas, and then the temperature is going to again not change. So when the temperature is not changing, the energy that we're adding is being used to break the attractions of the liquid particles to each other. This is water, and we know that because it's boiling at 100 and melting at 0. So what we're breaking are hydrogen bond attractions, one water molecule to another. Once that last attraction is broken here, then the gas temperature will increase again. And I can again demonstrate that for you in class, that the water vapor will increase in temperature. Another graph you need to be familiar with is called a phase diagram. Know the difference between the graphs. This graphic is called a heating or cooling curve. Heating or cooling curve. This graph is called a phase diagram. And what they're showing you here are the temperatures and pressures under which a substance exhibits a particular physical state of matter. So we have solid to the left, liquid, and then gas over here. I'm just writing those in because I don't know how well they print it on your paper. So the line that separates solid and liquid we know that solid and liquid, that physical change is called melting if we're going from left to right, and freezing if we're going from right to left. So this point here, this line here, this segment C that I have highlighted in red, that is called the melting point. So segment B from the triple point to point C is called the melting point. And you can see on our graph that as pressure increases, so as the pressure goes up and up and up here, the melting point goes down and down and down. So in this case, for this substance, as pressure increases, the melting point decreases. So increasing in pressure causes a decrease in melting point, which means if you take water, and this happens to be water because it's the only phase diagram where this is true, if you pressurize the water, it's going to be liquid at a lower and lower temperature. This is why ice skating rinks have to come out and smooth the ice, because you have this really thin blade going across the ice, making an extraordinary amount of pressure, melting the ice underneath it, and then that refreezes and we get these ruts and pivots. So they come out with their Zamboni. I've always wanted to drive one of those. They come out with their Zamboni and they spread water on the surface to smooth it all out with a big old water and squeegee system, and then it freezes again and we have our nice smooth ice. So the segment from triple point B to point D on the graph, that's representing the phase change between liquid and gas, or gas and liquid. So this is what we call the boiling point. And again, you can see that as the temperature increases, as the pressure increases, the boiling point also increases. This is the whole idea behind pressure cookers. What we do is we have a pot. The lid has a really tight seal. We put a teeny tiny hole in it to allow just enough gas out so the pot doesn't explode. But that creates an extraordinary amount of pressure on the surface of the water or the oil or whatever is in that pot. And by increasing the pressure above the liquid, that means that this is going to boil at a higher temperature. And when it boils at a higher temperature, our chicken cooks faster. Chick-fil-A uses oil pressure cookers. They have oil in the bottom. They seal it up, pressurize it as the oil vaporizes. The chicken cooks in a flash, and might I say, it is delicious. So segment BD represents, oh dear, I put that in the wrong spot, represents boiling point. Segment AB, way down here, a teeny little segment. That's the phase change. That's where the solid is going directly to the gas, or the gas is going directly to the solid. So that represents sublimation point. So in order for water to sublime, it has to be at really low temperatures and at really low pressures. You may have seen this occur if you had a bottle of water that you put in a really cold fridge, like way less than zero, and pressure inside the container is low, and then you open that up, and so the pressure in the container is like normal, and then you open the lid, and that depressurizes, and the water will turn to solid in the jar. I don't know if you've ever seen that, but it's a really cool thing. Or sometimes if you pour it, so you have this water, maybe it got hot, you put it in the fridge, it's pressurized in the bottle, you take it out of the cold fridge, open it up, it depressurizes it, and the water will turn directly to a solid from its, oh, I'm wrong. It's from its liquid state. That's still really cool. But that's not sublimation. That was a fail. But we will move on. So what is the pressure of the normal boiling point? So here's the thing, you guys. Normals, because these are changing, we measure a normal boiling point and a normal melting point. Notice that this is listed as normal, 101.3 kilopascals of pressure. And that pressure is significant because that is standard pressure. So if we follow that across and see where they hit the lines, that there is the normal melting point. If we drop a normal melting point, if we drop that down, for water, that's 0 degrees Celsius. Follow that pressure along to the gas and liquid barrier, and we see that that becomes our normal boiling point at 100 degrees Celsius. So water can boil at higher or lower temperatures for many reasons, one of which is a change in atmospheric pressure, and you'll learn about another later if we add particles to that water. So what's significant about the normal boiling point is that it is measured at standard pressure, and that's what we call normal, so measured at standard pressure. So if you're ever asked for the normal boiling point or melting point of something, and you have the graph, you should look for standard pressure. And on this graph, it is 101.3 kilopascals. That, of course, could be listed as 1 atmosphere. It could be listed as 760 millimeters of mercury, your favorite unit. Okay, so remember, this is called a phase diagram. This is called a heating and cooling curve. What I would like you to do is print the practice on the phase diagram from the website. It'll just say phase diagram practice. And I would like you to complete that so we can go over it. And if you will remind me in class to show you those things that I told you I would show you about the temperature of the gas increasing beyond 100 and the ability to pressurize a liquid and make it solid. Okay, thank you.